Okay, welcome to Math 150, Section 1, 2021. We're going to call this the 26th lecture so that it aligns with the lecture that this is being linked to from 2014. So today we're doing the root test, and then later we will do the integral test. So the root test is a bit more powerful than the ratio test, but it's more powerful sometimes in a stupid way, where I'll give you some examples where the ratio test fails, but I don't think it's really fair to say that it's a failure of the ratio test. So there's a couple of different ones you can do. I did some searching online, and one of the ones I found was the following. Let's let an equal 2 to the negative n if n is odd, and 2 to the negative n plus 2, which is 4 times 2 to the negative n if n is even. So if I want to do the ratio test, I need to calculate an over an plus 1. What do I have to be careful about when I'm looking at an over an plus 1? So one is if it equals 0, and we're not going to have that, so we're good in that sense. What else do I have to worry about if I want to use this definition? What do I need to know? Yeah, if it's odd or even. So how should we figure this out? What should we do? Do both of them. So this is very similar to Lagrange multipliers. For Lagrange multipliers, we often had to worry about, well, what if lambda is 0? What if this value of x is 0? The best way to handle it is to just break it into a bunch of cases. So case 1, n is even. And if n is even, then an, let's say n equals 2m. So we have a 2m over a 2m plus 1. What's that going to be? So a 2m is going to be, this case, it's going to be 4 times 2 to the negative 2m. And we would divide by a 2n plus 1, which would be 2 to the negative 2m plus 1. And so it's going to be 4 times 2 to the negative 2m, 2 to the negative 2m minus 1. It's going to be 1/2 2 to the negative 2m. So it's 8. Okay. What does that mean? So we just calculated that this is 8. What do you want to say? It diverges. Why does it diverge? What's greater than 1? Because you're very specific. So did we show that the limit is 8? Did we show the limit is always 8? What did we show? We showed the limit is 8 when n is even. Did we show that the limit is 8? No, we showed the limit is 8 when n is even. Let's look at case 2. N is odd. So let's write n as 2m plus 1. We would have a 2m plus 1 over a 2m plus 2. And so now, because it's odd, it would be 2 to the negative 2m plus 1 up top, and then down below it's even, so it's going to be 4 times 2 to the negative 2m plus 2. So it's going to be 1/2 2 to the negative 2m divided by 4 times 2 to the negative 2 times 2 to the negative 2m. So these cancel, the 4 cancels, and we get 1/2. Limit does not exist. Because the limit does not exist, we cannot use the ratio test. Now, when you look at this, it's either a great example or a stupid example, depending on how you feel. I think it's a nice example in that it gives a situation where the limit doesn't exist, so we can't use the ratio test. But what could we do if we wanted to understand the infinite sum? We can't understand the infinite sum by adding all the terms together, A1, A2, A3, A4, A5. How could we handle the infinite sum? What could we do? So we can't add them all in order, because the ratio test won't work for something like that. How could we try to add them? How would you like to group things? When we did telescoping sums, we saw things grouped nicely and canceled. How would you like to group the terms of the sequence? Yeah, group them into even and odds. Group into an even and odd. And if you take an even, you get 4 times 1 plus 4 times, when it is 2, you get 4 plus 4 times when it is, when n is now going to be 6, you would have 4 times 1/4 cubed. So if I write all the evens like that, is this sum going to converge? So will that sum converge? What do you think? If I just add the evens, is this going to converge? So how would you determine whether or not this series converges? Well, there's 2 natural ways to do it. Can you compare this to anything? What kind of series is this? This series has a name. It's a geometric series. What's the ratio? What's the ratio for this geometric series? 1/4, which is less than 1, so it converges. If you look at the odds, we get something very similar. So if I try to analyze the series directly, and I try to use the ratio test, it's going to fail. But if I just split it into the even and the odds, I can then get the ratio test to work. So I just have to split it and be a little bit more careful. So in that sense, it's not necessarily the greatest example, because with a little bit of work, I can pass from this to a new series where everything will converge. One of the reasons I can do this is because everything in sight is positive. We talked about the Fubini theorem earlier in the semester. When can you switch the order of integration? When can you switch the order of sums? And whenever you see infinities, you have to be careful. I was a little bit late for meeting with a student yesterday because I got an emergency call from a math teacher in the school district as their class wanted to divide 0 by 0 and they weren't sure what to do. They decided to call me rather than Alexa. I was very happy about this. And they knew it's dangerous when you divide anything by 0. When you have infinities, that is a danger sign. And so what I want to do now is I want to show you as an aside how dangerous things can be when you have infinities. So can somebody give me a series that diverges? An infinite sum that diverges. There's two natural go-to series. Okay, so 1 is odd to the n if r is greater than or equal to 1, which includes the trivial example 1 plus 1 plus 1 plus 1 plus 1. Okay, but r to the n with r greater than 1 is not the greatest example of a divergent series because it fails the test of the terms going to 0. Same thing with 1, 1, 1, 1, 1. So can you give me a series that diverges where the terms go to 0? One over n. So if I have 1 plus a half plus a third plus a fourth plus a fifth, this diverges. Now what I could do, 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth. I could look at this alternating sum. Do you think this alternating sum converges or diverges? First of all, do you think it's positive or negative? Positive. Why is it positive? We sub, right? And then the next term is smaller. And then 1/3 is bigger than a fourth. 1/5 is bigger than a sixth. So this is going to be greater than 0. Can you give me an upper bound? So it's at least 0. How large could it be? If it diverges, of course, the answer is infinity. But how large do you think this could be? Why 1?
Well,
Right, because as soon as I add the 1, the next two terms is negative positive. I'm going to subtract a little bit. And then negative positive, I'm going to subtract a little bit. And then when I add the negative 1/2, I get the half. Then I add 1/3, so I get up to 5/6. But first of all, I now know it's got to be greater than a half. And then when I add the 1/3, I know it would have to be less than 5/6. And so when I keep going like this, I'm actually going to get that the sum is going to converge. And it converges to a very interesting number, which we will talk about later in the semester. But what's nice is if you look at it as every two terms, you can see that the amount that you move is getting smaller and smaller and smaller. When I come over here, I know I've just added a positive number, so that's my new upper bound. And then I subtract 1/8, and I add more stuff over that. So I know I can't be further than 1/8 from where I am for the sum up to here. And so I know as I go further and further and further down, the bound between the upper and the lower sums is going to get smaller and smaller and smaller. So this is going to converge. There's a lot of nice ways to prove that it converges. One possibility is I can look at adjacent terms. So if I have two adjacent terms, I have 1/2 and minus 1 with a plus sign, minus 1/2 at the end. Okay, and I would sum this, n goes from 1 to infinity. And so here is my odd term with a positive sign, and here's my even term with a negative sign. How would you do 1/2 and minus 1 minus 1/2n? What would you do to do that algebra? So how would you handle that? By the common denominator, so it's going to be 2n minus 1 times 2n. I cross multiply I multiply by 2n over 2n, 2n minus 1 over 2n minus 1. I'll get 2n over their product minus 2n minus 1 over their product. So it's just 1 over 2n minus 1 times 2n. Right? What do you think is true about this sum? Do you think that sum converges or diverges? Why? What are you going to compare it to? Well, that would be a geometric series. So it's not decaying as fast as a geometric series. It's not a bad thing to try the geometric series. That's one of our go-tos. But there's something else we can compare it to. What does the denominator look like approximately? It looks like approximately 4n squared. It's 4n squared minus 2n. So with a little bit of algebra, this is less than the sum n goes from 1 to infinity of 1 over 2n minus 1 squared. I just made the 2n a little bit smaller, which makes the whole thing a little bit larger. We've seen this trick before of replacing some of the factors with something a little bit larger or smaller. What does this look like now, 1 over 2n minus 1 squared? This is 1 plus 1/3 squared, plus 1/5 squared, plus 1/7 squared, plus 1/9 squared. What series does this kind of look like? Or maybe a subset of the series. We have 1, 1/3 squared, 1/5 squared, a 7th squared, a 9th squared, an 11th squared. What does that sound like? The sum of well, geometric, you have to have to a power, right? You need to have some fixed ratio to a power. We don't have a ratio to a power. We don't have something like 1/2 squared, 1/2 cubed, 1/2 to the 4th. The power is always the same. It's always to the 2nd power. Yeah, so it's looking a lot like 1 over n squared. This is going to be less than the sum n goes from 1 to infinity of 1 over m squared. Here I just have the sum of just the odds, the reciprocal of the odd squares. So that would be less than equal to the sum of everything. And that's a p series where p is greater than 1, so it converges. So p series, p greater than 1, it converges. So if I look at this alternating sum, the alternating sum converges. So what's interesting is the initial harmonic series diverges. The alternating sum converges. If I added just the positive terms in the harmonic series, would that be infinity or would that be finite? We know the harmonic sum diverges. If I add just the positive terms, could that be finite? Which could the sum of the negative terms be larger than the sum of the positive terms in absolute value? No, because the positive terms are always larger than the one immediately after. So if the positive terms had a finite sum, the negative terms would have a finite sum, and that would contradict the sum being infinite. So if I just look at the 1, the 1/3, the 1/5, the 1/7, that sum has to be plus infinity. What if I looked at just the 1/2, the 1/4, the 1/6? I'll leave that to you as a similar argument shows that that also has to be infinite. So when I look at this alternating series, we call this the alternating series, the alternating harmonic series. We have the sum of 1 over 2n minus 1, and goes from 1 to infinity is infinity, and the sum equals 1 to infinity of 1 over 2n equals infinity. So if you look at the sum of just the positive terms, it's infinity. If you look at the sum of just the negative terms, it's infinity. Okay, but when we add them in this very special way, we get a finite sum. One of the things we love to do is we love to rearrange the order in which we do operations to try to make the algebra nicer. When you have an alternating series, a series with both positive and negative terms, you have to be very careful. This is one of the most common mistakes people make, is that they are a little cavalier, a little free with dealing with signed terms. We have to be extremely careful. And what I'm going to show you, and I sent you a video that does this for pi, is you give me any number, and I can rearrange the terms, the order in which I add them to converge to your favorite number. So if anybody doesn't have a favorite number, I have two numbers that I normally go to. 19. Any reason you want to share of why 19? Okay. Your birthday? Okay, 19 is a good number. So anybody else have a number? All right, I will do 24601. I was talking about that number with my daughters. So I'm going to have my sum alternate back and forth between those two numbers. And what you do is here's 19, here's 24601. We start adding the positive terms. So what we do is we keep adding the positive terms until we first exceed 24601. And so we add 1, that's a third, that's a fifth, that's a seventh. It's going to take a long time before we exceed this. And now what do we do once we exceed this? Now we add the negative terms, and we keep adding the negative terms until what? Until we first dip below 19. And now what do we do? And now we add the next positive term. So let's say the last positive term we added was 1 over 17 quadrillion. And 1, because it has to be odd. Then we would add 1 over 17 quadrillion, and 3, 1 over 17 quadrillion, and 5, 1 over 17 quadrillion, and 7. And we would keep adding positive terms until we again just exceed 24601. And then what would we do? Then we would add the negative terms until we just go below 19. So by doing this, I can reorder the terms so that my sum hops between any two values I want. If I wanted to make it converge, instead of doing 24601, I would just choose the same number twice. I would keep adding positive terms until I first broke 19, then I would take negative terms until I was first below 19, then positive terms until I was again above 19. So what happens here is for this sequence, you can add the terms and get any number you want by choosing the order in which you add them. So the video shows you a way to do it to get pi. But you can do this for any number. This shows you how dangerous it is to work with series that have plus and minus signs. So we talk about being conditionally convergent. Versus absolutely convergent. So something that's conditionally convergent converges with the order you have. Something that's absolutely convergent, what do you think absolutely convergent will mean? Always converges, and so when you put in the absolute value, it's still going to converge. So if we were to put in the absolute values for the alternating harmonic series, it will diverge. It will be just the normal harmonic series. As written, the signed harmonic series, the alternating harmonic series, is conditionally convergent. It's not absolutely convergent. And so I just wanted to point this out as a challenge. If you see positive and negative signs, you have to be careful. Now, on one of my exams, same professor, different class, when I was an undergraduate, I reordered the real numbers. And he wrote on the exam, I don't know what kind of magic you're using, Steve, but some serious magic is required for you to make this work. You can't just reorder the number line. And it's because of stuff like this that you have to be very careful. Normally, if I have a bunch of additions, is addition commutative? Does order matter for adding numbers? No, it doesn't matter. But if you have infinitely many, all of a sudden order can matter if you have infinity. And this is a great example of how infinities come out. Okay. So I want to turn now to just stating the ratio test. And so we have seen that it is technically more powerful than the root test, but it may not be more powerful than the root test with an intelligent person who can realize, I've got two series over here, can I just split them? So you would need a better example than what I gave to show that it's really stronger than the ratio test. So the root test. So let rho equals the limit as n goes to infinity of the nth root of the absolute value of an. And the limit as n goes to infinity of the absolute value of an to 1 over n. If rho is greater than 1, it diverges. Rho equals 1, no inflation. Rho less than 1 converges. So this is very similar to what we have with the ratio test. But it's very important to mention that when I write that rho equals the limit, I'm assuming the limit exists. Does the limit always have to exist? No. In fact, we saw an example earlier today where if I go and calculate the limit through the evens, I get 8, and if I calculate it through the odds, I get 1/2. So the limit does not always have to exist. So the ratio and the root test assume the limit exists. And if the limit exists, this is what happens. I'm happy to give a quick sketch of why this works. Do you want to do converges or diverges? We did converges last time. We can either do diverges to see the other one, or we can say we're going to be the convergence section. Diverges, okay. And then what will I do in section 2 today? I'll do converges, okay. So assume rho is greater than 1. So that means there exists a big N such that for all little n greater than or equal to big N, the nth root of an is greater than or equal to 1 plus epsilon for some fixed epsilon greater than 0. What does it mean for the limit to exist? Well, here's 1, here's rho. And we're saying the limit exists. That means eventually I have to be extremely close to rho. Yeah, that's what it means for the limit to exist. As n gets larger and larger and larger, this has to get closer and closer to rho. Well, I can choose a small number that's more than 1 and a little bit less than rho. So I'm outside that little window. And because I'm converging, eventually I'm in that small little box. And so if I'm in that small little box, I have to then be further from 1. How much further? At least 1 plus epsilon. So now let's look at what happens. So an plus 1 What would that be? What do you think that's going to go to? So as n gets very, very large, what do you think is happening to these terms? I'm sorry? So we know that eventually an to the 1 plus an to the 1 over n is greater than or equal to 1 plus epsilon. How could you rewrite this? Do you like taking the nth root of something? How could you rearrange the algebra? I don't like taking the nth root of something. So if I tell you the square root of something is 3, what's the number? 9. If I tell you the cube root of something is 3, what's the number? 27. So if I tell you an to the 1 over n is greater than or equal to 1 plus epsilon, what do you know about an? This is the same as what must be true about an. It's going to be greater than 1 plus epsilon to the n. So when I look at these terms, this is going to be greater than or equal to 1 plus epsilon to the n plus 1. This will be greater than or equal to 1 plus epsilon to the n plus 2, and so on and so on. Are the terms tending to 0? No. So because the terms aren't tending to 0, diverges. Doesn't go to 0. Okay. So this is a quick sketch of why the root test works. What are we comparing it to in the end? It's still a geometric series comparison. Everything comes down to the geometric series. When rho is greater than 1, the divergence is coming from comparing it to a geometric series that diverges. When rho is greater than 1, or when rho is less than 1, it's coming from a comparison to a geometric series that converges. Okay. So now it all comes down to, can you actually compute these quantities? So I will hold off on doing the root test problem for now. I want to talk about the integral test first. So assume an is either non-increasing or non-decreasing. So if it's non-increasing, then that means it never gets smaller. Somebody just got locked out. Give me something in life that is non-decreasing. Something related to yourself. Age, right? Any fans of the Big Bang Theory? One of my favorite moments is when Sheldon is getting Leonard as his roommate, and they're signing the roommate agreement. And one of the articles is that if either one of us ever invents a time machine, the very first place we will go to is right now. And after 5 seconds, Sheldon goes, oh, this is okay. So we cannot move backwards and forward in time. We only move in one direction in time. We are always getting older. Give me something that's sometimes increasing and sometimes decreasing function. Wait. Right? That can go up and down. So some quantities are not going to fall into either of these categories. They're not going to be non-increasing or non-decreasing. Some of them will fall into this very nicely. And if we do, then we have a really nice way of approximating. So assume f of x is such that, and I'm going to just be a little cavalier here. You can look at the book for the full rigorous statement. You can look at the video for the full rigorous statement. We'll assume that, say an is decreasing, and an less than equal to f of x less than equal to an plus 1, or n less than equal to x less than equal to n plus 1. Then the sum of ak, k goes from 1 to n, is basically the integral from 1 to n of f of x dx. And you can be a little bit more precise. You can talk about what the errors are. You can bound how much you're off by. But essentially what's going on, and we go through in great detail in the lecture that you watched, is here's my sequence. Here's 1, here's 2, here's 3, here's 4, here's 5. And what I'm going to do is here is maybe a1, here's a 2, here's a 3, here's a 4, and so on. And since, wait a minute, I'm saying an is decreasing, sorry. If an is decreasing, any of these going in the other direction. An greater than equal to fx greater than equal to an plus 1. And so my function, say, looks something like this. And because the an's are decreasing, and an greater than equal to f of x greater than equal to an plus 1 in this range, you can see that the sum of the an's is going to be a little bit larger than the integral over f. And so do you agree that the integral over f would be a lower bound for my sum? Now, if we wanted an upper bound, what we would do is rather than writing the first box going to the right, I would have the first box going to the left, like this. And then I would have the second box go like this in A2, and then like this A3, and this as A4. And now if we do that, the integral is going to be a little bit larger. And so now we know the integral from 1 to n of f of x dx is, let's go to the sum, k goes from 1 to n of ak, and that's going to be less than equal to, and so before, let's say n equals 4. Well, so if n equals 4, we really have to integrate all the way up to 1 more. So we would have to integrate up to n plus 1. And now if we go to the other direction, if it's 4, we would start over here at 4. So it would be a1 plus the integral from 1 to n of f of x dx. And so this is a really nice way to get a handle on the sum, is we can sandwich the sum between two integrals. And it's a little bit annoying that for this one you've got to go up to n plus 1, for this one you go up to n, for this one you have to remember there's an extra term. But really, it's the integral from n to n plus 1 f of x dx plus the integral from 1 to n of f of x dx less than equal to the sum goes from 1 to n of ak is less equal to the integral from 1 to n of f of x dx plus a1. So really, this is the part that really matters. If I add a little extra term a1, is that going to affect whether or not something converges or diverges? No, a1 is a fixed amount. And similarly on this side, if my function f is decaying, then my function f is going to have to be going towards 0 because we know f of x in each range is at most an. So what does this integral have to go to? As n gets large, what does that integral have to go to? It has to go to 0 because we know f is getting smaller and smaller and smaller. So eventually, this has to be getting close to 0. Goes to 0. So basically, the sum converges if the integral converges. The sum diverges if the integral diverges. So if the integral from 1 to infinity of f of x dx equals infinity, the sum diverges. If it's finite, it converges. And that's why I just wrote the squiggliness for the integral test. If you can just figure out what the integral is doing, you can tell if the series converges or diverges. But what's great is more than just does it converge or diverge, you can actually get a sense of the size. A1 is a fixed amount. This amount is going to 0. What this means is I can evaluate this sum, and my error is going to be at most a1. That's not bad. And if you wanted to get a better answer, you could do more work than that. Are people comfortable with this? So let's do the standard example. So you have to figure out what function to use. And in almost every case, it's replace n with x. So let's say I give you an equals 1 over n. What should f of x be? 1 over x. And so we integrate from 1 to infinity of 1 over x dx. What's the antiderivative of 1 over x? Natural log of x. And so in the upper level classes, we use LOG as and we evaluate this at 1 in infinity, and this would be infinity. But we can do better. If we wanted to sum k goes from 1 to n of of 1 over k, this is approximately the integral from 1 to n of 1 over x dx, which is just the log of n, and the error is at most 1. That's wonderful. We can now figure out roughly how fast is the harmonic series diverging. It's diverging very slowly. The log of n grows slowly. What's the log of e to the 100? 100. E to the 1,000. E to the million. Oh my God, your e to the million is only a million. This function is growing so slowly, it's going to be a long time before you see this. There's a nice application of this to trying to stack dominoes. And this is another thing lost during COVID. I can't remember if it was in this video where the students actually have dominoes. Was it this video? And you try to have the maximum overhang. And if you assume that each domino has to be to the right of the previous, then the answer as to how far you can go is the harmonic series. If you allow yourself to build in both directions, that sometimes it's better to take one step backwards to take 2 steps forward, you can actually do enormously better. Instead of going like log of n, it's like I think n to the the 1/2. And my first year math professor was one of the people behind proving results like this. And it's just really great because just instinctively, you often put on additional assumptions that just aren't there. We all do this. We all assume things about people, about situations, about problems that are not necessarily true. Nowhere does it say when you're stacking the dominoes that you have to build in just one direction. It seems like, well, if I want to go as far as possible to the right, why would I want to build to the left as well? Well, it sometimes helps you in terms of distributing the weight. So let's end with an interesting problem. How big is n factorial? And I love this because I can now have a sentence ending with an exclamation point followed by question mark and be grammatically correct. So n factorial is the product of all the integers from 1 to n. It's 1 times 2 times 3 times n. Any thoughts about how we should handle this? How should we handle this product? We have a product. It should be a Pavlovian response anytime you have a product. What is your go-to? Take a log. The log of n factorial is the log of 1 plus the log of 2 plus the log of n. This is the same as the sum k goes from 1 to n of the log of k. Is this sequence non-decreasing or non-increasing? It's non-decreasing. And in fact, in this case, it's even strictly increasing. Can anybody give me a function that I could use here? What should my f of x be? Log of x. So this is approximately equal to the integral from 1 to n of the log of x dx. And so again, as a rule of thumb, you just replace n with x. Now we need to know what function has derivative log of x. I think I gave this as an extra credit problem. It's x log x minus x. I do not expect you to be able to do this, but I expect you to be able to tell if this is right. How can you tell if it's right? Take the derivative. And so now, evaluate this at 1 and n. So we get n log n minus n. And then when n equals 1, we get the log of 1 is 0 minus 1 becomes plus 1. I'm running a little bit out of room. So we get the log of n factorial is approximately n log n minus n plus 1. So we get n factorial is approximately e to the n log n minus n plus 1. This is a chance to review some exponents. It's e to the n log n, e to the negative n, e. I'm going to write e to the n log n as e to the log n to the n, e to the minus n times e. And we'll review laws of exponents on Monday. But when you have the product of two exponents, e to the ab, it's e to the a whole thing to the b. What's e raised to the log of n? N. The log of n is how many powers of e I need to get n. I raise e by the number of powers of e I need to get n. This is similar to what is the sign of the arc sine of 1/2. Just 1/2. And so this is just going to be n to the n, e to the minus n times e. The correct answer is n factorial. It's approximately n to the n, e to the minus n, square root of 2 pi n. And the fact that there's a square root of 2 pi, it's related, if you've done statistics, to the Gaussian, to the standard normal, to the bell curve. There's a lot of really great math going on here. But this gives you a sense of the power of the integral test. Is not only is it telling us whether or not something converges or diverges, but in these special cases, it actually can give us some estimate of the size of quantities. And because we have a sense of the size, that provides a lot of additional information. All right, this is a good place to stop. We will continue on Friday.